In this tutorial on industrial instrumentation, we will talk about pressure measurement part 4. Here we will cover mechanical type or elastic type pressure transducers. The topics that we will cover here are Bourdon tube, diaphragm, bellow and piston. The elastic type pressure transducers or gauges are used to measure medium to very high pressure, sometimes as high as 700 megapascal. In this type of gauges, the fluid is enclosed inside a closed chamber having walls made up of elastic materials. At least one side is made up of elastic element in this type of gauges. The readout from these transducers can be either a direct physical dial-based output or in form of transduced electrical signals. The elastic transducers are costlier than their manometer counterparts and they are fragile and susceptible to system vibrations. There are mainly three types of elastic pressure transducers and a fourth one. They are Bourdon tube, diaphragm gauge, bellow, and the fourth type is piston type. The Bourdon tube is an elastic type pressure gauge which experiences deflection under pressure. The measurement range of the Bourdon tube is 0.1 to 700 megapascal. The tube walls have a thickness between 0.01 and 0.05 inches. This deflection is a function of the applied pressure. It is a fixed device having an opening at one end through which the unknown pressure is applied. The construction is elliptical in shape, bent in the shape of a semicircular arc, quite like the alphabet C, generally termed as C-type Bourdon tube. There are other shapes of Bourdon tube as well, like the twisted, the helical or the spiral. The bent angle of the C-type Bourdon tube is 27 degrees. The general construction material of the elastic medium of the Bourdon tube are carbon, chromium, nickel, molybdenum alloy, silicon bronze, phosphor bronze, beryllium copper inconel. The free end is attached to an adjustable link with pinion, gear and ring arrangements connected to a pointer that moves over a calibrated dial. The unknown pressure is connected to the free end and this pressure acts on the inner wall of the Bourdon tube. As the fluid pressure enters the Bourdon tube, it tries to be reformed, and because of a free tip available, this action causes the tip to travel in free space and tube unwinds. The applied pressure tends to straighten up the tube, which is either circular or spiral or helical in shape. The tube undergoes deflection which is proportional to the applied pressure. This deflection is read out by the gear, pinion, ring pointer arrangement. The pointer assumes new position with movement in the pinion section. The advantages of the Bourdon tubes are that they are capable of producing very high accurate results. The tube is low on cost and simple in construction. The output can be read out as electrical signals. They are capable in measuring very high pressure with adequate operator safety. The results are highly accurate even at very high pressure. The Bourdon tubes are low maintenance devices. There are few limitations of the Bourdon tube, which are that their speed of response is pretty slow. The device is affected by hysteresis errors. The device is susceptible to both shock and vibration. A certain level of output amplification is always needed for good interpretable readouts, and the precision in measurement of the device is on the lower side. The diaphragm pressure gauge is a thin circular chamber either made up of metal disc or flexible elements like rubber, leather or plastic. The choice of the body depends on the purpose of operation. The metal disc body exploits the elastic characteristics of the metal, while the flexible non-metal elements are opposed by the other elastic elements. This device, unlike the Bourdon tube, is faster in output response and also has high sensitivity. The pressure measurement range for the metal disc is 0.01 kilopascal to 7 megapascal, and for the flexible non-metal elements it is 0.1 kilopascal to 2.2 megapascal. The device is mainly used in low to medium pressure measurement. The device is connected to capacitive transducers or differential pressure gauges for output readout. The diaphragm can be flat, corrugated or like a capsule. Sometimes multiple capsules are cascaded together to enhance the measurement range. The diaphragm can handle corrosive environment and it is also suitable for slurry services. The materials of construction for the metal disc are stainless steel, inconel, monel, nickel, beryllium copper, silicon bronze, carbon chromium nickel molybdenum alloy, and phosphor bronze. The flexible non-metal materials are made up of polythene, neoprene, silk, nylon, teflon, Buna in rubber and leather. There are certain factors that influence the diaphragm measurement and they are the number of corrugations, the depth of each corrugation, the number of capsules used, the diameter of each of these capsules, the diaphragm material characteristics, and finally the wall thickness. The diaphragm operates in the following manner. The unknown pressure is introduced in the central position of the capsule or diaphragm. The pressure tends to push the thin walls of the corrugated device outward, causing deflection in the equipment. The maximum deflection is reported at the central position. The total diaphragm deflection is the summation of all the individual deflection recorded by each of the corrugations or the capsules. The deflection is observed on a pointer scale set up by a gearbox arrangement. The advantages of the diaphragm gauges are that they are of low to moderate cost. The device shows good overage characteristics. It does not register any permanent zero shift. They are suitable for both absolute and differential pressure measurement. The device has linear output over a wide measurement range. They are suitable for both corrosive environments and slurry services. The limitations of the diaphragm are that the device is susceptible to both shock and vibration. When continuously exposed to high pressure, it might damage the device permanently. The device maintenance and repair is tedious. Diaphragm gauges find application in medium pressure measurement, pressure draft in boiler chimneys. The third type in the family of elastic pressure transducers is the bellow. The bellow elements are thin-walled cylindrical in shape chambers containing many folds and convolutions. The bellow is a one-piece expandable and one-piece collapsible axially flexible device. With the application of pressure, axial direction of the bellow gets deformed by either compression or expansion. In a bellow setup, the unknown pressure is applied at one end while the other end is exposed to atmospheric pressure. The bellow can also be used to measure absolute pressure by evacuating either the exterior or the interior bellow space, followed by measuring the pressure on the opposite sides. Bellow can be connected to potentiometers as well. Bellows are used to measure low pressure less than 0.2 megapascal and have a sensitivity of 0.0012 megapascal. The construction material for a bellow are stainless steel, copper, phosphor, bronze, or trumpet brass. The bellows can be configured as cascaded capsules. In industry, bellows are made by turning a solid stock of metal, by soldering or welding stamped annular rings, or by rolling a tube, or by hydraulically forming a drawing tubing. For selecting the bellow material, the following factors are checked. That is, the pressure range under measurement, the hysteresis effects, the fatigue or dynamic operation, the corrosive environment, how much corrosive the environment is, ease of fabrication, and sensitivity to fluctuating pressure. The advantages that a bellow offers are that they are capable to measure both absolute and differential pressure. They are used in measuring low to medium range pressure. The cost is moderate to low. The limitations of bellow are that it is not capable to measure high pressure. Bellow joints are fragile and susceptible to catastrophic failures. In situ maintenance and repair is not possible in bellows. It requires ambient temperature compensation. The fourth type of elastic transducer is the piston type pressure gauge. This gauge has a magnetic piston and range spring in the bore of the gauge body. Differential pressure between the high and the low ports moves the piston in the bore against the range spring. The range of pressure measurement is 0 Pascal to 3000 kilopascal. The position of the piston is directly proportional to the differential pressure. The device is capable to withstand both shock and vibration. It is commonly used in hydraulic applications. The pressure output is given in electrical signals, that is in volt or ampere. For more reading, the readers can refer to the following references and links. Thank you.